Now, let us come to servo valves. They were typically developed for aviation applications, because in aviation you have to make very precise movements of these control surfaces of the aircraft against very heavy load, which is aerodynamic, because the aircraft is moving at huge speed through the atmosphere. So, very precise motion has to be created against high load. It is for these purposes that these servo valves were originally developed. It is a total closed loop control technology, because you do not want the characteristic to change, everything is very tuned, and well, you have all the previous advantages like electric drive, accuracy, computing interface, flexibility, programmability, and hydraulics for high power weight ratio. So, what is the basic idea? See a very typical very simple type of servo valve. So, what is happening here is that, suppose you shift this rod. Okay. So, if you pull this lever, it will move this way. As it moves this way, what is going to happen? That this port will be connected to this, and the tanks are at the end. Actually, you can imagine that the tanks are here. So, the return stroke is going to be controlled going to the tank. This is the way the fluid will flow. Now, interesting thing is, where is the feedback? Interesting thing is that the load is connected to the body. So, if you have pulled the spool this side, the cylinder will move which side? It will move this side. So, the load will also move this side, and the load is connected to the body. So, now the body will also move this side, this body, not the spool, the spool is connected to the lever and the body is connected to the load. So, the body will move. So, the movement of the body is actually like a movement of the spool in the other direction, because the flow, the opening is actually by relative motion. So, if the body also moves in this direction, again this valve will close. So, you see that at a particular position of the piston or a position of the load, this flow will again close. Till it closes, there is going to be flow and there is going to be velocity, and this load will keep moving this way. So, if you move the lever, the valve is going to move in one direction and then finally come and stop. That is by feedback. Okay. So, this is a typical very simple mechanical arrangement servo valve, right. There are various types of servo valves. For example, one may have a two-stage valve, right. So, what happens in a two-stage valve? Because you want to control huge power. So, the final stage valve is actually very large. So, even to move its spool, you need another servo valve. So, you see what is happening, you need an actuator. So, this is the first stage. So, this is the first stage. So, you give actually your control input here. So, accordingly, if you move it, if you push it this way, then this port will open and this port will open. So, the cylinder will move down. When it moves down, then what is going to happen is that this will get connected to this and this will get connected to this. So, this is the main valve, this is the pilot valve, that is, it is a valve which drives another valve, just like a pilot rides in front of a car, that is a pilot car. So, the pilot is actually the leader who drives. So, in this way, this is the driving valve and this is the driven valve, and this in turn, these ports may be connected, these two ports A and B will be connected to the main actuator, which may be a very heavy load, right. So, this way you get power amplification. So, here is a typical type of two stage servo valve construction. See what is happening. You have two kinds of pressure, note first. So, first of all you have where is the main valve and where is the pilot valve. So, this is the pilot valve and this is the main valve. This is the first thing to note. Who moves the pilot valve? This solenoid. Actually, this is connected to the spool, which is not shown. So, let us identify the parts, right. And so, what happens is that suppose you tilt the solenoid, something like a torque motor arrangement, which we will see what it is. This will push this valve this way. Now, you see that there is a control pressure. So, the control pressure will come and this valve will move to this end. So, the pressure will fall here, come here and come here and come here and create a pressure here. So, you see that here what is the pressure? Here the pressure is PC, but here the pressure is not PC because it has to drop through this valve. So, this is going to be less than PC. In fact, so then if this side is PC and if this side is less than PC and still this has to move this way, then the net force here has to be more than the net force here. Therefore, the areas must be controlled. So, the area here is actually twice A and the area here is A. So, for moving this pressure is only required to be PC by 2, the pressure here is only required to be PC by 2. So, the moment this rises above PC by 2, this valve will shift this way. Now, when this valve will shift this way, you see that this is the final actuator, this is the motor. So, then when this valve will move this way, then what will happen is that probably this port will get connected to here and this port will get connected to here. So, then you will get pump and tank connected to the motor. Now, where is the feedback? The feedback is here in this thing, this is the feedback element. So, this spool is going to push this thing this way. When it pushes, here is a fulcrum, see fulcrum. So, this will again push the spool, not the spool, the sleeve. So, the spool is being pushed by this one and this feedback element pushes the sleeves. So, it is going to push the sleeves this way. So, again the relative motion, this motion of the sleeve will nullify the relative motion of the spool which was created by the current. So, again at a certain position, at a certain gap, again this will become PC by 2. So, now when the moment it becomes PC by 2, there is no force on this and it will come to stop. So, it is at that position that now when it comes to stop, then there is a certain amount of opening here and depending on that so when you have a certain amount of opening, you have a certain amount of flow, you have a certain amount of pressure. So, you are going to drive the motor at that flow rate or that speed. So, this is the operation of the two stage servo valve. This shows that this is a slight little analysis of that feedback arrangement, that is, if the suppose you have this is a valve and this is an actuator and there is a connecting link. So, you give an input motion here, what will happen? this will initially shift this way. The moment this shift this way, what happens is that the pump connects to this and the tank connects to this. So, the actuator moves this way. When the actuator moves this way, the W moves this way and that will tend to keep it put it up. So, so the cause that was created, the effect will nullify the cause, that is why it is a negative feedback situation and it is stable. So, if you want to analyze the motion of this Z which finally creates the flow, then you have to understand that, then you have to look at it like this. So, you see that first when you imagine that first there are actually two inputs and this is the motion that you want to analyze. So, first of all you apply superposition. So, first of all you assume that W is 0 and X is applied. So, then this rod is going to move about this because W is 0. So, pivoted to this, that will create some motion. Next you imagine that X is fixed and W is moving. So, now you imagine that it is moving like this about X. So, this is, so if you can, for small motions you can imagine that these two motions are the motions which will be created and the net motion is going to be a resultant of that. So, now you can understand. So, if W is the fulcrum and if X is applied, if an amount X is applied, then what is going to be the motion here, right. So, that is going to be B by A plus B into X. On the other hand, if you apply fix it here and apply a motion Y here, this is Y, then what is going to be the motion here? It is going to be A by B into W, suppose W is the motion here. So, finally you get, so for what is the final motion Z? So, you have an effective feedback arrangement where what is coming, this is the motion created by the motion X, this is the motion created by the feedback W and this is the net motion Z at any point of time, and that is going to create, so a motion creates a flow and this is the flow gain. So, that is going to create a volumetric flow that divided by AP will give you the linear motion, AP is the area of the piston, that integrated 1 by S will give you the motion of the plane W. So, this is the control system that is effective and here is the transfer function. So, the transfer function between, you can see that now that the transfer function between Y by X is actually in the steady state S is going to go to 0. So, it is going to be A plus B by A and it will act like a first order transfer function. So, this is the basic dynamics of any feedback of you have seen various kinds of linkage type of feedback arrangements. So, this is the basic analysis of one such feedback arrangement and in a typical case such analysis can be made. Next we see another type of servo valve which is a flapper type servo valve. So, you see what is happening here? What is happening here is that again here this is the valve. The valve is being moved by applying pressure here or pressure here. So, you have to create a differential pressure. How do you create that pressure? As such, this is also this is a 1000 psi, this is a restrictor. So, it is a pressure reducing valve. So, simply a series of obstructions. So, the pressure will, while flowing, the pressure will drop here and it will be something like 500 psi at these two ends. When this is a flapper nozzle, okay. So, if there is a minuscule motion of this flapper, then the pressure at this point is going to rise if it is this side and the pressure at this side is going to fall. So, that will create a differential pressure and it will move the spool. This is the basic principle. And how do you create this motion? You create this motion by what is known as the torque motor coil. So, you have a what sometimes called a torquer or sometimes called a torque motor, which can create a minuscule motion of this flapper. The advantage of flapper nozzles is that their gain is very high, there is very small motion can create a very high pressure difference. So, they are very sensitive devices. The next is a, so you here you see get to see the construction of the torquer. So, you see that this is the construction of the torquer. So, when what happens is that you create an S pole here and an N pole here, and N pole here, S pole, that is the way it is wound. So, and so what happens is that now you have this pole shoe. So, if you send currents like this, then this is going to repel and this is going to attract. So, this torquer will slightly tilt, it will slightly tilt, and it is this tilt which will be, this is connected, this is the flapper plate. So, this is the way you control the flapper. This is a picture, Moog is a very is a company which is a very well known manufacturer of such valves. So, this is just a picture from their website. This is a cross sectional view of a direct drive valve. So, you can see that the various parts, this is the electronics, this is the actual valve, and this is the what is known as the coil which will pull the spool, and here is the position sensor which is typically an LVDT. You sometimes have a spring here, and this is where you make the connection. So, these are just to show you the various parts, the actual geometric, how they are packed into a very, these are very, very compact devices. How do you do closed loop position control? So, very simple, this is a this is a position loop. So, you have a proportional or servo valve here that is driven by this electronics and moves the load. This is the cylinder which the position of the load is sensed by the position sensor. This is the position, typically an LVDT, sometimes a potentiometer, could be a resolver if it is rotary, and these two are compared, this and the error is fed. So, standard position loop. This ramp generator is sometimes used because the fact that you do not need to saturate the amplifier, and you want to, heavy loads should not be, should not give jerks to them, that might create the damage to your equipment, might give damage to the load. So, therefore, whenever a position signal has to be changed, sometimes you need to control the rate at which it should go. You never give step signals generally to these kind of systems. So, you have a ramp generator. If you want to go from one system to another, you go slowly through a ramp, which depends on the velocity level that you want to have on this load. This is a block diagram arrangement of the valve, of that loop. So, you see that these are the electrical gains. These are the electrical circuit gains. This is the sensor gain. This is the valve gain. So, this is current. This is the current to flow characteristic KQ of the valve. So, when you have a certain flow, then that flow is going in. So, flow by area will give you velocity, and velocity integrated will give you position. This is like a block diagram. Similarly, the flow that you are having, this which you are assuming that is going through because of your nominal value of KQ that you know, sometimes that this flow can be slightly changed if the supply pressure of the pump changes. So, to model that, they have put a pressure disturbance block. So, if you want to, because these are I am sorry, because these are very precision control devices generally. So, this it is important to understand the dynamics, because there is so much load acting on it that so much force acting on it that this dynamics can actually affect. For example, in an aircraft the dynamics of the actuator is very important. So, in an electrohydraulic aerospace actuator you have a similar block. So, you can see that you have, this is the final say control surface, this is a typical actuator used in aerospace, very precision actuators. This is the cylinder which is sometimes called a ram. This is, so the cylinder is driven by a servo valve, the servo valve is driven by a force motor, and the force motor, this is the coil which drives the spool of the valve, and that is driven by the electronics and the servo amplifier. So, there are various feedbacks. There is a current feedback which is inside this, force motor current is sensed and fed back beyond here. Then there is a spool position feedback of the hydraulic servo valve spool, and finally there is a ram position feedback of the actual control surface. So, these are connected in cascade loops. You can see we will not do it in much detail, but the typical drive electronics. So, you use, all that I wanted to show is that you have to, there are certain elements, for example, you have to use servo amplifiers and V2I converters, and then you need various kinds of filters, because specifically because you want to avoid giving inputs to your system which may cause things like resonance. So, for that, from that point of view, you have to cut out certain frequencies in your input, and that is why you need various kinds of notch filters. So, this name is a load resonance notch. So, if you are carrying molten steel using a hydraulic system, then there is certain natural frequency. If you give input at that frequency, then the molten steel will spill over. So, you have to cut out that frequency, so that as you are transferring, there will be no waves created in the liquid steel or whatever. For these purposes, certain frequencies of inputs must be cut out. So, this is a typical if you see the spool dynamics, it is very simple. There is some force acting on the spool which is created by the coil. This creates a certain amount of acceleration. So, this is acceleration, this is velocity. So, you have friction feedback, and then this finally spool position, and you have two kinds of feedback. One is that you can have a spring, sometimes we have seen that we have centering springs connected. So, you have spring force, and you have a Bernoulli force which is occurring, which is a force on the spool because of that fluid flowing through the valve. So, there is some force acting on the spool. So, these act as feedback elements. So, this creates the motion of the spool. Similarly, in the ram, the motion of the spool, the flow into the ram depends on the supply pressure and the spool. So, you see that this is the inlet fluid into the ram, and what is the outlet fluid? If the motion of the ram is x ram and this is the area of the cylinder, then this is the fluid which is going out. So, there is a little difference finally, and that difference actually causes what creates the force? The force is created by the compression of the fluid. So, initially there is a little fluid compression, and because the bulk modulus is so high, so that immediately creates a lot of pressure, and that multiplied by area. So, you get the force, that is the acting force on the cylinder. There is a load on the cylinder also. So, the difference actually accelerates the cylinder and creates the motion. So, this is the kind of dynamics that you have on hydraulic cylinders, and they have to be precisely controlled. So, we have come to the end of the lesson. We have seen flow, pressure and control valves, we have seen hydraulic cylinders, proportional valves, servo valves, and some hydraulic actuation systems. Last points to ponder. What is the difference between a servo valve and a proportional valve? Is it in terms of feedback? Is it in terms of performance accuracy? Is it in terms of structure, drive, what? Identify the major components of a hydraulic actuation system. This is one of the major, this question you should be able to answer, because this is one of the basic purposes, basic instructional objectives. sketch the construction of a two-stage servo valve. This is going to take some time, but think about it, how it works, especially how the feedback works. Why are pilot operation of valves needed? Can you think of some actual application? And explain the operation of a flow control valve. That is interesting, how the flow is controlled irrespective of pressure variation by a mechanical arrangement. So, that brings us to the end of our lesson today. Thank you very much.